Hello and welcome to this video where I will look at the mark scheme of the IGCSE paper 4 variant 1 of the year 2020 May-June session. And let's go straight to the first question. On the right hand side I have the question paper, and then on the left hand side I've got a board or a blackboard where I'm going to ink that blackboard where there is a calculation to be done. So any writing that we're going to do, we are going to do it on the left hand side. And let's go straight to the first question. Now in this question, we are asked the following. We are told that an aeroplane of mass 2.5 by 10 raised to the power 5 kilograms lands with a speed of 62 meters per second on a horizontal runway at time t is equals to 0. That means that when it lands, that is when we start timing. And remember, it lands with a speed of 62 meters per second. And because it's moving in a straight line, we can say it's got uniform velocity of 62 meters per second. That is its initial velocity. The initial velocity is the velocity the object has when t is 0, when time is 0. Let's see what happens. The aeroplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 meters per second at t is equals to 35 seconds. So v is the final velocity, which is 6 meters per second. So because the velocity has decreased, there is the word deceleration. And this velocity changes from 62 meters per second to 6 meters per second in a time of 35 seconds. So we've got u. Let me just write the details for that particular part of the question. So here we have question 1. So here we have question 1. And we have u is 62 meters per second. We've got v, which is 6 meters per second, and that change occurs in a time of 35 seconds. And you can see A is asking us to calculate deceleration. Calculate the deceleration of the aeroplane in the 35 seconds after it lands. Now let me just remind you that when when it comes to calculation, we actually do not calculate deceleration. What we actually calculate is acceleration. Then if that acceleration has a positive value, we leave it like that. But if the acceleration has a negative value, we call it deceleration, as follows. So here in A, part 1, we are going to calculate the acceleration. The acceleration is the change in velocity, which is given by the final velocity minus the initial velocity, of course, divided by the time. So v minus u over t. Our v is 6, so it's important to identify the v and the u. And of course this one is 35. And you'll see this one automatically will give us a negative sign because we are subtracting a bigger value from a smaller value. And let's see how much that one turns out to be. So over here I'll have 6 minus 62 and I get minus 56. Of course, that one, when I divide it by 35, divide by 35, I get minus 1.6 meters per second squared. You must indicate the units. You can see that the units have not been indicated there. Now that is not the end of it, because I've worked out the acceleration. In order to answer the question, you can see the question requires me to write down the deceleration. And we have just agreed that if the acceleration has a negative sign, you call it deceleration. As follows. So my answer will read like this. The deceleration, of course, I don't have to repeat the word deceleration because it's already written for us here. I just need to write the value there. It's going to be equal to 1.6 meters per second squared. And here I've got to be careful to leave out the negative sign, because the negative sign has been taken care of by the word deceleration. When we say that the deceleration is 1.6 meters per second squared, it means that the velocity of this aeroplane is decreasing by 1.6 meters per second every second. Number one, it is a decrease. And then by how much? And then at what rate? Per unit time, how much does it decrease by? So what do we learn from this question? From this question, we learn how to identify the various physical quantities as far as linear motion is concerned, where we learn that the velocity the object has when we start timing is referred to as the initial velocity. The velocity the object has after a particular duration of time or interval of time is referred to as the final velocity, v. And by the way, the symbols are u and v for initial velocity and final velocity. And then we learn something else, or we remind ourselves something else. How do we work out the acceleration? Acceleration by definition is the rate of change of velocity, or change in velocity per unit time. How do we work out change in something? Change in something is always equal to the final of that physical quantity minus the initial of that physical quantity. That is how we calculate a change in that physical quantity. So the change in velocity is the final velocity minus the initial velocity. And then we also remember that when it comes to acceleration, to calculating deceleration, there is no equation for calculating deceleration. We always calculate the acceleration. And then, if that acceleration has a positive value, we leave it as acceleration and we call it acceleration. But if the acceleration possesses a negative sign, then we call it deceleration. And I've just stated its meaning. So the velocity is decreasing by 1.6 meters per second by a velocity of 1.6 meters per second every second. Let's look at the second part. The second part is about the resultant force acting on the aeroplane as it decelerates. So there is definitely a force here which is acting on the aeroplane. So part 2 of A, we have to calculate F is equal to MA. This is the equation which is used to calculate the resultant force acting on an object of mass m, producing an acceleration A. So again, notice that it is the A that we always use, not the deceleration. Let the negative take care of itself. For example, over here, the mass is 2.5 by 10 raised to power 5. That is the mass in kilograms. and the acceleration is negative 1.6 meters per second squared. Let's see what we get from there. So I'll just get 1.6. I multiply it by 2.5, and here I get 4. I get negative 4 by 10 raised to power 5 newtons. Or the other unit of force is kilograms meter per second squared. Like that. The negative sign means that this force is acting in the opposite direction. The resultant force on the aeroplane is opposing its motion, is acting in the opposite direction to which the aeroplane is moving. So if the aeroplane is moving to the right, that resultant force is acting in the opposite direction. And remember the meaning of resultant force. It is that unbalanced force. So let's look at the question and see whether we have answered that question. The resultant force acting on the aeroplane as it decelerates. So at this point, we can just state it is minus 4 by 10 raised to power 5. You will not be penalized for forgetting the negative sign here, because the negative sign I've already stated its significance, that it is acting in the opposite direction to the direction in which the object is moving. So that is how I would work out that part. Let me look at part 3. In part 3, I'm required to work out the momentum of the aeroplane when its speed is 6 meters per second. How do we work out momentum? Let me get a new slide to enable us to do that. I need several new slides. I'm going to put them in that position so that each and every time I need one, I just click at that point and I use it. So this time I want to use a new slide over here, and part 3, want to work out the momentum of the aeroplane when its speed is 6 meters per second. This is like the final momentum. Momentum has got the symbol P, and because I'm talking about final momentum, I'm going to put a subscript F there, meaning final, or I can just write a complete word final as a subscript. So it's going to be equal to the mass of the aeroplane times its final velocity. The mass of the aeroplane, we have seen it is 2.5 by 10 raised to power 5 kilograms, and its velocity is of course 6 meters per second. 6 meters per second. And again, I want to multiply just 2.5 by 6, and that gives me 15 by 10 raised to power 5. 15 by 10 raised to power 5, which is equal to 1.5 by 10 raised to power 6 kilograms for the mass, and then meters per second for the velocity, or Newton seconds. Elsewhere, we have seen that the unit of momentum can also be Newton seconds. Remember, momentum is a vector quantity, so the direction of this final momentum is to the right, because the plane is still moving to the right. Then part B, let's quickly go to part B. At time t is equals to 35 seconds, the aeroplane stops decelerating and moves along the runway at a constant speed of 6 meters per second for a further 15 seconds. On figure 1.1, sketch the shape of the graph for the distance traveled by the aeroplane along the runway between t is equals to 0 and t is equals to 50. You are not required to calculate the distance values. We just need to sketch the shape of the graph for the distance covered. So let's see, when t is equals to 0, its velocity was 62 meters per second. And when t is equals to 35, its velocity is 6 meters per second. So its velocity was decreasing. So let me just draw my axis over here. This will be the y-axis, indicating the distance d. This will be the x-axis. Let me just try to draw straight lines, although they are usually very difficult to draw, but that one is approximately okay. This one is 0. I'm going to put my 35 here and 50 over here. So over here the velocity is very high. Over here the velocity is less. And here it's moving with a constant velocity. Between 35 and 50, it's moving with a constant velocity. I have to remember that the gradient of a distance time graph, because this is time, distance time graph gives me speed, and I want to make sure that this speed is constant. So I'm going to have a straight line to get constant speed. And then from there, I'll have to curve. That one is not a very good curvature. Even this one is, I think it is leaning too much or inclined too much. Let me see what I can be able to do with that. I'm going to indicate this 35. Let that 35 be somewhere around here, because I want to do a little bit of carving out. So I'm going to have straight line like that. Then over here, that looks comfortable. Remember, the gradient of a distance time graph represents speed. So because here the speed is very high, the gradient must be higher. That is why it is very steep here. And over here, the gradient is 6. So it is less. And here it means that it maintains that constant speed. That's why here it is a straight line, while here it is curved like this. So that is how we will draw a distance time graph for the motion of the aircraft. Next, let's see whether there is another part. There is definitely another part, part C. As the aeroplane decelerates, its kinetic energy decreases. Suggest what happens to this energy. You see, as it decelerates, as its speed decreases, its kinetic energy automatically is decreasing. Okay, and that happens between 0 and 35 seconds. Its kinetic energy is obviously decreasing. What is happening to this energy? Of course, we know that that energy cannot be lost, because it will contradict the principle of conservation of energy. It cannot just disappear into nothing. It must be converted into another form of energy. That is what this question is asking us to calculate. So one of the forms of energy that is very obvious here, there is friction between the surface of the aeroplane and the air. And friction results in the bodies becoming hot, warm. So that is another type of energy. It is heat energy. So that kinetic energy is being converted into thermal energy or heat energy, or you can say it is converted into internal energy of the surrounding air, or the heat energy of the bodywork of the aeroplane, because the aeroplane must become a little bit warm. That is the surface of the aeroplane. The other type of energy is due to the friction between the tire and the ground, because the aeroplane cannot solely rely on the air resistance in order to slow down. If brakes are applied, you will find that there will be friction between the tire and the surface of the runway. That frictional force again gives rise to heat. So there is friction force between the tires and the surface of the runway, and the friction force between the surface of the aircraft and the air. Both of these, they are going to result in heat energy. And that heat energy will be absorbed by the tire itself, by the road, by the air, and by the bodywork of the aeroplane. So that is what we can say about that question for 10 marks. If you argue out like that, then it follows that you're going to get all the 10 marks. Let's quickly recap what we've been able to learn in this particular question. Number one, we've been able to review the concept of, kinematics. How do we get acceleration? How do we calculate acceleration? Then dynamics. How do we use Newton's second law of motion, F is equals to ma, to calculate either the resultant force, the mass, or the acceleration? Then the other part is, of course, about momentum. Of course, for that part, there isn't much problem other than remembering that momentum of an object is defined as the product of its mass and its velocity. The definition is not required here. It is simply the equation for calculating momentum. And finally, it's about the change in energy of this particular system. When you look at this question, there are so many things that it has left out. For instance, when we calculated the force and we noticed that the force had a negative sign, that force that was causing the deceleration, we could refer to that force as the decelerating force or the retarding force. If the examiner asked us to calculate the retarding force, then we will forget about the negative sign, because the word retarding takes care of the negative sign. It already indicates that is the force that is responsible for the retardation. By the way, the other word for deceleration is retardation or retardation. And that is what we can say about this particular question. In the next video, I'm going to look at question number 2. So stay tuned.